gravity, we're going to learn that at Earth's surface, the weight of an object is mass times the acceleration of gravity. We're going to do lots of problems, free body diagram problems, where we get to do that. Then we'll talk about mass versus weight, which is a conceptual issue. And then finally, we'll talk about the acceleration of gravity on other planets and how you can get them pretty easy, or how you can get an object's weight, given the relationship between the planet's mass and radius and Earth's mass and radius. Well, let's get started. Here we go. You guys learned Friday. Here's a second. You learned Friday Newton's law of universal gravitation. The fact that Newton figured out that that gravitational force is proportional to each of the masses, and it's also inversely proportional to the square between the square of the distance between the centers of mass of those masses. He didn't know what G actually was, but later on we learned that G has the value of 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. Yesterday at the end of the period, or Friday at the end of the period, I asked you what the gravitational force between two 1 kilogram objects held 1 meter apart is, and you found that it was almost a trillionth of a Newton, which is an incredibly small, almost pretty much unmeasurable force. So that's why it's not difficult for me to hold two objects apart that are both 1 kilogram. They're not like striving to get with each other, because the gravitational force between them is so teeny tiny. I'd like to try something else now. I want you to get the gravitational force that is the weight of an object of mass m at Earth's surface. Get the weight, which weight is another name for gravitational force. Get the weight of an object of mass m at Earth's surface. Well, in order to get the weight of an object of mass m at Earth's surface, you need to know some things about Earth, correct? For example, here's Earth, okay? And here's the object of mass m. The distance between the object of mass m and the center of the Earth, which is my r, is going to be the radius of the Earth. And of course that m1 is going to have to be the mass of the Earth. m2 will be the mass of this object. So the weight on the object is going to be g times the mass of Earth times the mass of the object over the radius of the Earth squared. Well, I'm going to give you those values, and then I'd like you to do the punchy. That is, use G is 6.67 times 10 to the negative 11th, use the value for the mass of the Earth, which is approximately 5.98 times 10 to the 24th kilograms, and use what we know about the radius of the Earth, which is 6.38 times 10 to the 6th meters. Plug in those values and see what you get. And for the m2, that's just m, the mass of the object. And I want you to do it and get the wonderful feeling of recognition after you get through punching those numbers. Who's the first one who's going to recognize? What is g times the mass of the Earth divided by the radius of the Earth squared? What do you get? So anyone want to tell us what you got? Fatima, what did you get?
9.8.
How many people are getting it? 9.8. Is that a familiar number to you guys? Good. You know, there's a reason why the acceleration of gravity at Earth's surface is 9.8 meters per second squared. And that reason is because this times this divided by that squared is 9.8. That's it. That's why. Right? You end up with 9.8 meters per second squared times the mass. So generally, the weight of any object at the surface of the Earth is going to be the mass of the object times the acceleration of gravity of Earth, 9.8 meters per second squared. And I do have this need to demonstrate for you that the units work out okay, right? You've got g times the mass of the Earth over the radius of the Earth squared, and g is 6. I'm just going to do units. G is Newton meter squared over kilogram squared. Mass is kilograms. Radius squared is meters squared. I hope you see that the meters squared cancel, and that this kilogram cancels one of those kilograms, and I'm left with just newtons per kilogram. But newtons is kilogram meters per second squared. So the kilograms cancel, and I'm left with just meters per second squared, which is the units of the acceleration of gravity. Yes?
For the answer 9.8, what is the m to the side of it?
The m, when I plug into this formula, it's g m1 m2 over r squared. This is m2. This is the mass of the object, which I haven't told you, so I'm just calling it m. But I want you to see that no matter what the mass of the object is, whether it's your mass or my mass, I can get the weight that the Earth, the force that the Earth exerts on me, which is my weight, by just doing 9.8 times our mass, whatever your mass is or whatever my mass is. You see? And so that gets us to this big equation we're learning, the first force that we're learning about. And that is generally, weight, which is the force that the Earth or any planet exerts on you, is going to be mass times the acceleration of gravity. Whatever the acceleration of gravity on that planet happens to be, mass times that acceleration of gravity is going to be your weight. And so we normally just write it weight equals mg. I'm going to give you some problems involving free body diagrams. Oh, okay, good. Oh, that's right. If you eat, it's going to show up. The cameraman, I just want to tell people, the camera person is eating while doing this, and so you're going to hear crunch, crunch, crunch. But that's okay. So here's a scale. I'm hoping I'm assuming no one watches these videos except you guys, so I don't care, I don't want to be an internet sensation. Okay. So here's a 1 kilogram mass. Here's a scale, a Newton scale. How many newtons is this 1 kilogram mass going to weigh approximately? Or exactly? How many newtons should this 1 kilogram mass weigh?
9.8.
You guys thinking 9.8? Heck yeah, 9.8, right? You guys okay with that? Yeah. And I want you to see this just visually. Is this saying 9.8? And you're seeing people like, yeah, it's 9.8. Okay, so approximately 10. It's just if I move it around, I can make the, But yeah, 9.8 approximately. And so generally, you multiply the mass by about 10, and you're going to get your weight. Okay? Let me ask you this question. What if I had a 27 Newton weight? Would there be a convenient way for me to figure out how many kilograms that 27 Newton weight weighed? What would I have to do with that 27 newtons? What would I have to do to that number? Yeah, many people thinking divide by 9.8. Yeah, sure. And we can see that right here. Right? If weight equals mg, then mass is going to equal weight over the acceleration of gravity. Right? So let me ask you this question. let's say I wanted a 1 Newton weight. How many grams would weigh 1 Newton? Knowing that 1 kilogram weighs 10 Newtons, how many grams would weigh 1 Newton? Approximately. What's a, oh please, how many kilograms weighs 1? If 1 kilogram weighs 10 Newtons, how many kilograms weighs 1 Newton? Thank you very much, Noel. Say that louder so the camera.
0.1.
Thank you very much, 0.1. And how many grams is that?
100.
Yes, thank you, Noel. Thank you for saving us. Yeah, 100 grams. This is 100 grams, and this is approximately 1 Newton. You guys okay with that? 100 grams is 1 Newton. 1 kilogram is 10 Newtons, approximately. It's actually 9.8. Let me ask you another question. This is a question that nobody in the second period knew the answer to. One person knew the answer to this in third period. I'm just curious how many people in fourth period know this. 1 kilogram of mass. How many pounds is that?
2.2.
How many people think it's 2.2? Okay, so there's like 5 or 6 of you who know that. Good, good job. Cheyenne. 2.2. What's that? Okay. Yeah, 2.2 pounds. So let me ask you this question. Would you rather have a kilogram of gold, a pound of gold, or a Newton of gold? Which would you prefer? A kilogram of gold, a pound of gold, or a Newton of gold? And obviously you want the most. You ready to vote? How many people here would rather have a kilogram of gold? Okay, most of you. How many people say a pound of gold? Okay, how many people say a Newton of gold? Because you don't really care about money, and so money corrupts, and so it's harder for a rich man to go to heaven than for a camel to go through the eye of the needle. So you don't want to be too rich, so you went with 1 Newton. But because remember, one Newton is approximately 100 grams, which is, 1 Newton is a tenth of that, 0.22 pounds. So 1 Newton's approximately a quarter of a pound. So yeah, obviously you go with the 1 kilogram because that's 2.2 pounds. Does anyone know what a metric ton is? Or do you know what a normal ton is? 6? No, how many pounds? Not 1,000 pounds. Not 10,000.
2,000.
Yeah, 2,000, right? One ton is 2,000 pounds. And so you've got this idea of a metric ton. And a metric ton, now easy, and what you were saying is correct. A metric ton is 1,000 kilograms. A metric ton is 1,000 kilograms, which makes it 2,200 pounds. But, we like metric, and so we would rather, but we like tons. And so you get this weird situation that people talk now about a metric ton, which is 1,000 kilograms, but it's pretty close to what a ton is. So when an American talks about tons and a European or in anything else in the worldian talks about metric tons, we're talking about the same amount, more or less. I mean, if I had a, okay, great. So anyway, that's weight equals mg. So now let's go ahead and apply this to our free body diagrams and our sum of the forces equals ma problems. Okay. Here comes our first example. A 500 Newton rocket ship experiences 450 newtons of upward thrust. Find its acceleration. And I want both magnitude and direction. Well, I'm going to show you the way I want you to do this problem, and then I'm going to have you guys do one on your own. Here's the way I want it done. Number one, I want a free body diagram. Here's my rocket ship. It's experiencing it's a 500 Newton rocket ship, so its weight is 500 Newtons, but if you want, you can just call it mg. You're going to find that every problem, when there's weight, I just call it mg and I worry about what it is later. Or if you want, you can call it mg equals 500 Newtons, whichever way you want to do it. But I'm going to have a tendency of always calling weight mg. It experiences 450 Newtons of thrust upward. And I'm going to define up as the positive direction for this free body diagram. Please notice that my forces are always emanating from the free body. The next step is always to write sum of the forces equals ma. In this case, it's the y direction. That's the only direction I've got. Secondly, I want you to enumerate what these forces are. Don't just add the forces in your head and write down that one number, because most of the time there will be several forces, and many of them will be variables. Many of them you don't know what their values actually are. So you're going to have to write down every force. So I got 450 minus 500 Newtons. By the way, why am I subtracting the 5? What is it about this force vector that makes me want to subtract it? Yeah, it's pointing down, and up is positive, so anything pointing down, it gets to be negative in my equation. Mass, I never tell you what the mass of the rocket ship is. I know its weight, it's 500 Newtons. What am I going to have to do to that weight to get what its mass is? What's that? Come on.
Divided by,
Thank you very much. Divided by 9.8. Remember, if someone gives you mass, you multiply by 9.8 to get the weight. If someone gives you weight, you divide by 9.8 to get the mass. So here we go. So this is going to be 500 Newtons divided by 9.8. Gets you my acceleration. Now let's do the punchy. 0.98. Negative 0.98. By the way, what's the meaning of the acceleration being negative? What does that mean for me?
It's not going up.
Is it accelerating upward or downward? It's accelerating downward. So my thrust isn't enough to keep my rocket ship up. My rocket ship is crashing to the earth. So the acceleration is 0.98 meters per second squared down. Okay, you guys ready to do a problem similar to this? Okay, let's see how smart you are. I'm going to give you a significantly harder problem than last period because you guys are so much smarter than last period. Woo. I'm kidding, of course. You're all the same. You guys are all the same. I'd like to ask you. Okay, here we go. A 320 Newton block. Oh wait, no, I don't want to do that. Wait. A block of wood is feeling 320 Newtons of buoyant force up. Oh, and immersed. I'm sorry, I'm making up this problem as I go. And immersed in water. So I've got a block of wood that's immersed in water. Okay? So you know wood floats. So if I have it at the bottom of a swimming pool, that block of wood is going upward because it's lighter than, less dense than water. So an immersed in water block of wood is feeling 320 Newtons of buoyant force and accelerates upward at 0.27 meters per second, find its mass. Good luck. How are you going to do this? Same way. Free body diagram, sum of the forces equals ma. Good luck. It's just different stuff is known and unknown, that's all. Oh, do you guys know the buoyant force points upward?
Yeah.
I'm so sorry. Like I said, I shouldn't make these problems up just off the top of my head, right when I'm doing the lesson. Upward. It's a great problem that I just thought of. I wish I thought of it before. Okay, I'm gonna walk around and make sure you guys are doing free body diagram, your little microscopic free body diagram. Okay, what's the force acting downward? Where's that? There's a force acting downward.
So would you just assume that the gravity?
Yeah, mg. Hey guys, can I give you a heads up? Mg is acting downward.
Okay.
You should give me a free body diagram with the downward acting force is mg. Big left hand. What you got? Mg acting
Not the
downward.
right one.
31-ish.
Not the right answer.
And on the left side of the equation, it's got
How do you get the right answer? Bro, I know it's not the right answer.
I got 11.
You got it right there. It's gotta be 3
That's what I
20
got.
minus mg equals that thing that's all for m. On the left
Yeah.
side, 320.
Whoa.
1,185.
Good for you, Father. How you do you feel? Cool out there.
I don't know what it is.
How are you doing? Okay, good. You gotta label your free body diagram, 320 mg. You must label your free body diagram. You're not gonna get told. Where's your free body diagram? What? That's like microscopic. I can't even see it. Maybe if I take a picture of it and like explode the picture.
Explode.
Okay.
Oh my God, I love
Except make bigger lines. Okay, that arrow doesn't, you don't put accelerations in the free body diagram, only put forces.
Net force.
So there's only two forces. Don't put X and Y direction forces, there are none. Just, I mean, X direction forces, only Y.
You don't know
So
the
320 up, mg
My
down.
doctor, I had the picture.
Okay, beautiful. Okay, now do sum of the force equals ma, and on the left side will be 320 minus mg. Where's your mg? Gotta be mg down. Then on the left side of the equation, 320 minus mg. Oh, you poor kids. You're like sheep without a shepherd.
Minus 7G. Energy. Oh.
Good.
Yeah.
Good. Beautiful. If you do the math right, you win. Your free body diagram is bad. You need this. I need the big fat dot. You don't even have a big fat dot, and then have mg down. When you have mg down, think about
You're looking at what
it. Cool is a very good skill. Good. Good. Okay, the left side has to be 320 minus 7. You've got two forces in that line. Okay, beautiful. I don't know what
But isn't it not negative?
Okay, great.
Like,
No, but then you have to therefore, my assumptions are incorrect.
I got the equation. The left side of the 320 minus 7.
is
Between minus mg, the left side should be. Oh, you did it.
it what we, the force that we exert. That's our weight.
You're gonna have to get
First, can I still?
Yeah. I just moved the M to the other side. I just factor out. Okay, so you know, I just what's the priority?
Does anyone get picked? Because people were asking, like, since I'm an old member,
Well, this ended up being a lot tougher than I thought it would be. Hey guys, let me show you how to do this. First of all, your free body diagram must have all the forces acting on this wood. Okay, so here's my piece of wood, the big fat dot. I've got 320 newtons acting upward, and then even though my block of wood is in water, that doesn't mean Earth's gravity somehow gets canceled or something. I mean, Earth's gravity didn't suddenly go away just because the block happens to be in water or air or on a truck or wherever, right? You're still going to have gravity acting on it. So you've got mg acting down. I'm going to define up as positive, and then we do the sum of the forces equals ma. And when you look at that sum of the forces, you're going to look at your free body diagram. I've got two forces on this free body diagram, so don't be putting just 320 for F. There's two forces, 320 and mg. They got to both show up on the left side of this equation. So I got 320 newtons minus mg equals m times the acceleration, which is 0.27 meters per second squared. Okay? There, you will have gotten most of the points for this problem. Now, some of you are horrible at math, and so you can't solve for m. I'm going to show you how to solve for m. So I got mg plus m times 0.27, right? So I'm going to get rid of the units. So do you see I have 9.8 m plus 0.27 m? Which means I can factor the m out and have 9.8 plus 0.27. And so now I'm going to divide both sides by 9.8 plus 0.27. Okay, I'm going to make this darker. So 320 divided by the quantity 9.8 plus 0.27. 31.8 approximately. You guys okay with that? So you have to have this capability. Whenever you have a situation where something's at the surface of the Earth, then the weight of the object will always act straight down, and you've got to include that in your sum of the forces equals ma. Okay. Well, let's go ahead and talk about mass versus weight now, and let's talk conceptually. Okay. Mass versus weight. Okay. Suppose I'm in outer space I'm not near any planets or stars, so I'm in outer space. I'm just floating in outer space, okay? And I see in front of me two anvils, two identical looking anvils. Do you know what an anvil is, right?
Yes.
Big black cast iron thing that you put your horseshoe on and bang on it and make metal things in the Old West, you know? There's your anvil. So I see two anvils and they look identical to me, but there's a difference. Should I get in the middle here?
Oh, no, you're fine.
Okay, thank you. But there's a difference. One of them is made of styrofoam. So I've got a real anvil and a styrofoam anvil, and I need to figure out which is which. So I float on over to them, and I put my hand under each of them to see which weighs more. Is that going to work for me? No, because how much do they weigh? Zero, right? There's no planets or stars nearby. They weighed zero. I put my hand under both of them and I don't have to exert any force to have them remain in their position because they're floating just like I am. So tell me, what can I do to these anvils to determine which one is real and which one is fake? What? No, let's go and say it. Okay.
He said hit him.
You say hit them, right? Sure. Now, let's say that the styrofoam anvil is coated with hard plastic. So if I like hit them or snap, you know, kind of smack it, they're going to feel the same hardness to me. Okay. So tell me more. Let's say I hit them. What would I expect to have happen with the anvil versus the styrofoam? Yes, Cheyenne.
No, I was gonna say find the mass. I didn't.
Okay, well that's our whole point. We're trying to find which one is more massive. So how are you going to do that?
The styrofoam one will probably go farther.
Say that again.
The styrofoam one will probably go farther.
Good. Why? Is there some formula we learned that Isaac Newton taught us that might imply that it would go farther?
Yes, but I can't recall it.
Okay, who can tell me? Because if I'm going to smack them, let's assume I exert the same amount of force. So I go, and I go, okay, same amount of force. Which one? Why is the styrofoam guy going to go farther? Yeah, less mass. And which formula are you thinking of? F equals, thank you, Zena. F equals ma, right? F equals ma. Whichever is the real anvil, when I punch it, it's not going to go very far because it has a tremendous amount of mass. Whereas the styrofoam, when I punch it, it'll go hurtling off into deep space, right? Because it doesn't have much mass, so it'll have a high acceleration. Well, this little thought experiment is my big example of what mass is. Mass is a measure of an object's resistance to changes in its motion. That's what mass is. Mass, the measure, and can I be more specific? The quantitative measure of an object's resistance to changes in its motion. The real anvil has more mass, so it's not going to want to change its state of motion that readily. It's not going to want to go flying off if it has so much mass. By the way, an object's resistance to changes in its motion, what word do we use to describe or to define an object's resistance to changes in its motion? Yes, Sean?
Isn't it inertia?
Thank you, it's inertia. So mass is also a quantitative measure of inertia. That's what your mass is. If you're in elementary school and the teacher's trying to teach you about mass, then they're going to say something like how much matter something has. How much matter does it have? How many atoms does it have? How much matter an object has. That's their mass. And it's measured in kilograms. Here in physics land, we measure it in kilograms. How about weight? What's the definition of weight? What's that?
mg.
Good, mg if you happen to be at Earth's surface. But generally, what's the weight? Yes? Great, great. And what kind of force is it? Okay, good. But generally, like Newton's law of, yeah, gravitation. This is gravity force, yeah. It's the gravitational force that a planet or a star exerts on you. That's your weight. Gravitational force. From planet or star if you happen to be standing on a star. And what's the units of weight? Yeah, newtons. Weight is newtons. Weight is a force. Newtons. So mass and weight are two different things. Let me ask you something. My mass, am I able to, if I went from here to somewhere else, to deep space, to the surface of the moon, would my mass change?
No.
Yeah, no way. How much matter I have doesn't change. But could I change my weight? Let's say I'm here on planet Earth, okay? Is there somewhere I could go to make myself weigh less? Well, I want to remind you, gravitational force is Gm over Re squared, right? Here's Re. Is there somewhere I could go where I would weigh less?
Closer to the center.
Okay, close to, like, bury under the ground and get closer to the center? That's true, but that's a lot of work. What's something I could do that's not so much work?
Bring yourself into space.
Okay, getting in a plane, or where else? Because I want to get far from the center of mass. How about go on top of a mountain, right? Why should I do diet and exercise when I can lose weight by just going to the top of a mountain? I increase my distance from the center of the earth, and so I lose weight. Ta-da, boom, done. Okay? So I want you to see that weight depends on where you are. Your weight depends on where you are, which planet you're on, and how far away from the center of that planet you are. But mass is the same everywhere. Your mass doesn't change depending on whether you're on a mountain or at sea level or on the moon or anywhere. Your mass is going to remain the same, but your weight totally changes. Hey, let me give you a quick conceptual problem about this. Then I'm going to have to do a quick a mathematical problem, which you'll see momentarily. Earth, moon. I have two identical cars, same mass, same everything. They're on two identical surfaces. The only difference is one's on the moon and the other's on the earth. And I want both of them to have the same acceleration. I want them to both have the same acceleration. Now, of course, you know, the moon has 1/6 of the gravity of Earth. I want to know which requires more force. Do I need more force to obtain that acceleration on the Earth, or more force to obtain that acceleration on the moon? Are you guys ready to vote? Which requires more force? I'll give you three choices: Earth, moon, or the same force. How many people say, I need more force to accelerate that car when I'm on the Earth? Okay, so we got 1, 2, 3, 4 of you. How many people say I need more force to accelerate that car because when I'm on the moon? Okay, how many people say it's the same? Wow, got a lot more votes this time for the same than any of my previous periods. Anais, why did you say the same? Oh, okay. Pusha, why did you say the same?
Because acceleration is force over mass, and so the mass is the same anywhere, so.
Alrighty, so she's just going, hey, Mr. Shana, you just taught us F equals ma, force over mass, or what do you say? Acceleration's force over mass, and they got the same, what was I saying? Same acceleration and same mass, and so it's going to take the same force, F equals ma. Good. Here, let me draw you a drawing. Here's the weight of this car on the Earth. Here's the weight of this car on the moon. Why are you guys telling me that it takes the same force to accelerate them? Look, Earth's gravity is way more than the moon. Someone tell me, what do you notice about those gravities? What do you notice about the acceleration?
They're in the vertical direction.
What's that?
They're in the vertical direction, not horizontal.
Say that again.
They're in the vertical direction, not horizontal.
Imani's saying they're vertical, not horizontal. Why should I care about that? What is the relationship between these two directions? Oh, please, do I have to pull it out of you guys? Is the fact that this car weighs more on the Earth going to have any effect on anything that happens in the horizontal direction? Heck no. No, it doesn't matter, right? I could be on the surface of Jupiter, doesn't matter. You see what I mean? It's going to take the same amount of force to accelerate that mass the same amount if I'm accelerating it horizontal. That was the issue they had with the Earth rover, that car that the astronauts Apollo 11 that they rode in when they were on the moon. Did I say Earth? I meant moon. The moon rover. They're, the lunar, I think they called it the lunar rover or something. But anyway, they had to make a car for the astronauts to drive around the moon on, right? And they had to make an engine for that car. And the engine for the moon car had to be just as big as it would be for an Earth car. Even though the moon has only 1/6 the Earth's gravity, they still had to make the engine just as big because it's the same situation whether you're on the Earth or the moon. Okay? Hey, let me ask you one more question. Now I've got this guy, he's going to lift this car up. Tell me, what takes more force, to lift the car on the Earth or lift the car on the moon? Okay, someone tell me why. Why does it take more force to lift the car on the Earth? Yes?
More gravity.
Thank you. There's more gravity on the Earth. Now you're working against gravity. Now gravity matters. Okay? That's like the difference between weight and mass. Okay, there's one more problem I need to show you. You go to a different planet. You go to a different planet. This is example number 3, I guess. Has twice Earth's mass and twice Earth's radius. You go to a different planet, has twice Earth's mass and twice Earth's radius. You weigh 500 newtons on Earth. What's your weight on the other planet? So I'm telling you that your weight, which is g times the mass of the Earth times your mass over the radius of the Earth squared, is 500 newtons. And now do I go to a new planet that has twice Earth's mass and twice Earth's radius? Tell me how much you're going to weigh on that new planet. If the bell rings, don't go, because I have to actually show you how to do this problem. Anyone have a guess before I show you? Chris?
250.
Chris says 250. Does anyone agree with him? Okay, Chris, how'd you know it's 250?
Because the radius was squared, so then that would give me 4, and the mass was 2, so that's 1/2 of the weight.
Great, you guys okay with that? Let me show you the process you're going to go through. When you do this problem on tonight's homework, just substitute in the new values. That is, they tell me I got twice the mass, 2m. They tell me I got twice the radius, 2r. But now you're going to have to square that 2r. So I get 4RE squared, and then you take the 2/4 out. And this quantity, you know what GMEM over RE is? 500. Right, there it is. 500. So I got 1/2 times 500. And that's all you'll do. When you see a problem like that, just start with Newton's law of universal gravitation, plug in what they gave you, and then factor those numbers out. And then what you've got left over is the weight of the guy on Earth. So hey, good luck on tonight's homework. Are we